this beaker has a volume of 2 liters. I ask you to look at this beaker right now, because if you look at it right now, you just learned how big 2 liters is, and you cannot unlearn it. You may forget it. Those are 2 different things. Okay? And you can see that there's a bar spinning in there. And as we look down at the bar, is the bar spinning in a clockwise direction or counterclockwise direction? Can you see the bar
Clockwise.
spinning? It's going this way, right? Or this way?
Different.
Which way?
Clockwise.
Clockwise or counterclockwise?
Clockwise.
You're getting me confused here, okay? So I look at it and it's moving in this direction, okay? Now I want you to visualize the same bar, but you're looking up at it. Imagine there's a ceiling fan up there, and do what he's just doing over there, and tell me if this movement that you told me is clockwise. When you look up at it, what do you see?
Counterclockwise.
What do you see?
Counterclockwise.
You're getting me confused. Is this my right hand? I look up at it. Look up, it's my right hand, okay? Put it down here. Is it my right hand or what? Still my right hand. So what's going on? What's going on is that you and I know the code. If you find a glove, you can instantly tell whether it's right-handed or left-handed, right? Why? You know the code, right? Right? You know the code here too, but you have to think about it a little bit more. So I'd like everyone in the room right now, everyone, including me, stick your finger out like this. Okay? And rotate your finger in a clockwise direction. Hey, I said clockwise, what are you doing? I'm doing clockwise, watch me. See, I turn around like you, right? Clockwise, right? I'm not changing, watch me, I'm not changing. What do you see me do now?
Counterclockwise.
Okay, so you get the point? The perspective, the vantage point is very important, making all these observations. And of course, this notion of handedness is related to our DNA structure and all kinds of other things that we do in science. And by the way, where does this idea of this notion of clock movement comes from?
Clocks.
Clocks, oh yes. So where does it really come from?
Sundial.
Comes from the sundial. And as far as we know, was the sundial first used, invented and used, as far as we know, in the southern hemisphere or the northern hemisphere?
Northern.
As far as we know, it's in the northern hemisphere, right? So what I'd like you to do is to visualize the sundial in the southern hemisphere. And think about the movement there and decide whether it's clockwise or counterclockwise, all right? So all kinds of different things. But let me get to the experiment, because that's what we're going to do here. So in this experiment, I'm going to take 3 clear and colorless liquids and mix them together in this 2-liter beaker. Here's the first liquid. And then I take the second liquid. And I add the second liquid. Anything interesting happen so far?
Sort of cloudy.
Getting cloudy. Liquid is getting cloudy. And you can see now by increasing turning, maybe you can see the vortex a little bit. And you can see the volume has increased. You know, that's not very interesting, right? That's kind of expected. But it's not really expected every time you mix 2 liquids together, right? There are other forces that are involved there. Now I take the third liquid, and I add this one. And I get this beautiful color change where I end up with this beautiful blue color.
Whoa. Whoa.
What?
It's going back and forth.
What's going on? I don't see what's going on here. Look, the last time I looked at
Whoa.
the beaker, you're not paying attention to me anymore.
No.
The last time I looked at the beaker, it had in it a liquid that was blue in color. So tell me when to look. Should I look right now?
No.
Yeah.
No, don't look right now. Okay, don't. I'll listen to it.
Now.
Right now. I don't want to
Yeah.
trip over anything here. Should I look right now or not? Yes
Yeah.
or no?
Yes.
Right, you're sure? I
Yes.
should look right now.
Not anymore. No.
Absolutely? Yes or no?
No, absolutely.
Right this minute. Right this second. Blue, deep blue, almost black. Maybe you can help me better on this side. Tell me when I should look at it. Now? Or not? Yes? Huh? I'll look
Goes
right
back and
now?
forth.
Right this second. Don't want to trip over anything here, because there's no accidents now. Every time I look at it,
Never
it's
seen
blue.
this.
What are you doing that I'm not doing? You're looking all the time? I'm looking all the time. I'm looking at you all the time. What are you looking at all the time? You're looking at the... Whoa, wow, look at that. I see something that you were seeing before. This is called a chemical oscillating reaction. It's one of about 50 known such reactions, but this one is very special. It's special for two reasons. The first reason is that it was discovered by two high school teachers. It's named after them. It's called the Briggs-Rauscher chemical oscillating reaction. Briggs and Rauscher taught high school chemistry and physics in Northern California. And in 1973, they published a paper in the Journal of Chemical Education describing this beautiful, captivating behavior that we see right here. The second reason it's special to me is that it took researchers, high-powered researchers, members of the National Academy of Sciences. It took them 9 years to figure out what's going on in here. That's why we do research, because we want to satisfy the curiosity that we have. There are 24 elementary steps involved in there, in this beautiful color change sequence. And the chemicals are water, hydrogen peroxide, potassium iodide, malonic acid. I'm going too fast for you to write them down, but I'm just saying what they are, okay? There's potato starch in there, the sulfuric acid, I mentioned that. And the yellow color we see now is the color of iodine, what we say in the vernacular iodine. Combines with the potato starch, gives this nice blue characteristic color, and the oscillations keep going and going on until the reactants have been consumed. The overall reaction is the decomposition of hydrogen peroxide, 30% hydrogen peroxide. It decomposes to water and oxygen gas. Okay? So if you see some bubbles, it's because of that. Okay? There are also some carbon dioxide bubbles coming from the malonic acid that's in there and so on. All kinds of catalysis taking place in there. It's just a fascinating system. And it's used to catch attention. And it's used as a point of engagement in conversation. You might think that the people who were watching, in the slide I showed you, were watching this one, right? But they weren't. They were watching something else. But that's the same reaction we get whenever this is done. You also notice that when I did the experiment, before I did the experiment, what did I do? I put my goggles on. In case you didn't notice it, I just told you. So, anyway, this has been a very long presentation. I appreciate your being here. Thank you for coming especially for this, Dr. Lane. You've been a hero of mine for a long time. You've been a mentor to me, and we're still friends. So